All right, folks. Well, welcome back. I hope you folks had a restful day yesterday. Um, I think let's go ahead and just get started here. We will finish up with this problem set. So the problem set here, there's just about three more problems that we have to do. So I want to go ahead and start with this one here. So number two here in your problem set, folks, let's go ahead and get started with this. This is a review problem. I am anticipating that we should be back in time with plenty of time for the final. So I do expecting that we will be taking the final at school. So with that said, then this is a review problem. Let's go ahead and work this problem out, and then I'll work it out for you. Okay, so number two in your problem set, folks. Let's go ahead and let's get this done. Okay, let's go ahead then and let's work this problem out together. I'm sorry, let me go ahead and reset the clock quickly. That's the wrong one. Okay, let's go ahead and work this problem out. They want us to write the net dynamic equation. Remember, with the net dynamic equations, these are all double displacement reactions. And so with the net dynamic equation, or for any type of equation, we're going to identify the driver. And for these net dynamic equations, then we can go ahead and identify the ions that will form the driver for the reaction. Remember, the driver is either going to be a precipitate, a solid that forms during the course of the reaction, a gas that forms during the course of the reaction, or a molecule. And typically, that molecule will be water. So in reaction number one, in the very first reaction, what we see then is the driver for this reaction is going to be the formation of barium sulfate. Folks, make sure you remember the solubility rules. I know that that's something that you'll need to memorize for my class, for this class here, but for later on, if you decide to go and take AP chemistry or high level chemistry, it's very helpful that you have the solubility rules memorized. Okay? All right, so here's our ionic compound. This is the solid that forms. This is our precipitate here. This is the driver for the reaction. Okay, so we want to identify then the ions that go into making that driver. And so therefore, barium ions, and make sure you write down the charge, because this is an ion that is floating around in aqueous solution. Okay, so there's where the barium ion comes from. It comes from barium nitrate. All nitrates are soluble. Excuse me. All nitrates are soluble. And so therefore this barium is free floating around in the water before it reacts. And then when the sulfate is added from the sodium sulfate, and sodium sulfate is aqueous because of the sodium ion, okay, these two get together, they form the solid here, okay? All right, so with that said then, you don't have to write out the complete ionic equation, you just have to identify the driver, and the driver will be this precipitate here. Okay, then with the balance, now that you have the skeleton equation with these net ionic equations, again, remember, you have to balance out the atoms, and then you got to balance out the charges as well. And if you notice here, let's go ahead and count atoms, barium, there's one on each side. Remember, with polyatomic ions, we're going to count that as one unit. So we have 1 unit of sulfate on the left, 1 unit of sulfate on the right. The sulfates balance out. And if the polyatomic ions balance out, make sure you remember the atoms also balance out, okay? All right, the last thing we want to do then is balance out charges. 0 net charge on the left, on the right here, sorry. And we have 0 net charge on the left, 2 plus here and 2 minus. That makes a 0 net charge. There is your balanced net ionic equation, okay? All right, let's take a look at the second reaction, okay? Identifying the driver again in the second reaction. The driver then is the formation of silver chloride as a solid. Okay, so there's your precipitate. That's what's going to drive the reaction to completion. And so therefore we identify the atoms on the ions on the right that formed that particular atom. And so therefore we will get the chloride from the aluminum chloride. Okay, so the chloride ions come from aluminum chloride, and the silver ion is going to come from the silver nitrate. So we have then Ag plus. Now remember, with these ions here, you got to remember the charges on these. Okay, yes, this is a transition metal here, but remember I did mention then that there are a few of these transition metals that are that we'll only see for the most part single charges on them: silver, gold, and we talked about zinc as well. So silver and gold are going to be a +1, and zinc is going to be a +2. So make sure you keep that in mind. All right, so chloride here is a -1. It's a non-metal, will always have that charge. Okay. All right, so let's go ahead and balance out the atoms then. The atoms are balanced. the silver one on the left, one on the left, one on the right. Chlorides, chlorines, one on the right, one on the left. The atoms are balanced and the charges are also balanced. A -1 here and a +1 here will be a net charge of 0. Net charge is 0 on the right. Okay. All right. Let's go ahead then. Let's take a look at the third one. Okay, the driver for that reaction then is going to be the formation of water. So the driver then is going to be the formation of this molecule here, which is water. Okay, and so now we have to identify the atoms, the ions that form that particular molecule. Remember, this is the net ionic equation, so there has to be ions that form this molecule here. And so the hydrogen ion will come from the acid, sulfuric acid, and so we'll learn more about acids in chapter 19. That'll be part of the next unit. When we start, hopefully, chapter 13 on Monday, we're going to start looking at gases. The gases, and will be part of our next unit. We'll start out with the states of matter, and then we'll get into gases in chapter 14. But after that, we get into our discussion, our unit on acids, bases, which will begin with the solutions. Okay, so we'll get to this, and we'll get to acids here. But with that said, then remember I did mention that acids are ionic compounds with hydrogen as the cation. Okay. All right. And so therefore, the hydroxide will come from magnesium hydroxide, and so that's the formula for hydroxide. And there are the ions that make up water. Okay, so the two hydrogens one comes from the hydrogen ion, one comes from the hydroxide ion, and there's your oxygen. Okay. All right, so let's make sure then, so the driver here is the formation of water. So these are the driver. This is not a precipitate, but this is a molecule. Now, there will be other molecules that will form. We'll see that these molecules will also form. But typically, what you'll see in this class then is water forming during these double displacement reactions. Okay. All right, so let's go ahead and balance out atoms. We got 2 hydrogen atoms on the left, 2 hydrogen atoms on the right, 1 oxygen atom on the left, 1 oxygen atom on the right, so the atoms are balanced. And then finally, then with charge in, plus a +1 here, -1 here, 0 net charge on the left, 0 net charge on the right, because it's a molecule. Okay. Okay. So make sure you review that, and make sure you combine. And during our classroom session, during our Zoom tutorial session, you get extra help with that. Okay. All right. What I'd like you to do then, so that was the review of what we did back in chapter 11. Let's go ahead and review what we did, what we've done so far in this chapter here. So go ahead, go grab your book really quickly, okay? And you'll need your book for this. Hopefully it's close by. If not, pause it, pause the video, and then go get it. And what I'd like to do is take a couple minutes, work out number 16 from your book. On page 364, let's do number 16 from your book, and then I'll work it out with you. Okay, so make sure you write out do the work on your paper, and let's see what you come up with. Okay, all right, I'll go ahead and get started on it. Okay, let's take a look at number 16 then. Number 16 then, they give us this particular balanced equation right here. So they give us the balanced equation already, okay, as 3 nitrogen dioxide gas plus liquid water. It'll produce for us nitric acid, HNO3, 2 moles of nitric acid, and nitrogen monoxide, 1 mole nitrogen monoxide gas. Okay. All right, so that will balance out the equation for us. Okay, and so let's go ahead then and let's do the conversion. Okay, so this is the conversion that they're asking us to do here. And what do we start out with? So remember, when you do conversions, when you do stoichiometric conversions like this, you always want to start out just like with all the other conversion problems that we've done. Ask yourself the 3 questions. What do they give us to start out with? What are we solving for? What do they want us to solve for? And what conversion factor will get us from start to finish? So in this particular problem here, they give us 5.00 times 10 to the 22nd molecules of NO. That's what they're telling us. They're telling us, okay, if you have this amount here, how much of the nitrogen dioxide was needed? So that's the conversion. So let's go ahead then and let's write that down. Okay, so remember, just because these are the reactants doesn't mean that we're always going to start out with those. Here the problem is asking us if we end up So actually, the starting quantity here is 5.00 times 10 to the 22 nitrogen monoxide molecules. So that's what we're starting with. And that's why I wanted to do this problem, because I think some of us are going to get into the habit of thinking that we always will be given reactants and we're going to solve for products. And that's not always the case. Remember, when you're doing these conversions, ask yourself 3 questions. What are you starting out with? What do you want to end up with? And what's the conversion factor or factors that'll get us there? So here we are told then that we have 5.00 times 10 to the 22nd molecules of nitrogen monoxide. And what are we solving for? We are solving for grams of nitrogen dioxide. That, folks, is our conversion. And that's why I want us to do number 16, because you have to make sure you understand you will not always be given reactants and you're not always going to solve for products. All right, so with that said, I think this conversion here after that was pointed out to you would become pretty straightforward. So we have here number of particles, and so our first conversion factor then will be Avogadro's number. We'll divide by Avogadro's number. It's going to be 6.02 times 10 to the 23rd particles, molecules of nitrogen monoxide. Second conversion factor is going to be then the mole ratio between nitrogen dioxide and nitrogen monoxide, and that's going to be a 3 moles of NO2, 1 mole of nitrogen monoxide. Please make sure, if you're not quite, you don't see why we have to set up these conversion factors like we do here, make sure you come by and get some extra help with that. Okay, so then we have 46 grams then, molar mass is the last one. Right, 46 grams of nitrogen dioxide. Make sure you're clear on where we get this number from, over 1 mole of nitrogen dioxide. All right, and that's it. So you set that up then, and so you end up with 11.5 grams of nitrogen dioxide. So make sure you understand this. What we answered here was we answered then how much of this reactant did we need to start out with in order to form this amount of nitrogen monoxide. But what they did was, in this problem as a conversion problem, they gave us how much of the product formed, and then they asked us to find out how much of the reactant we started with. Okay, so kind of odd there, but like I said, if you remember how to approach these conversion problems, it ends up being a little bit more straightforward. Okay. All right, very good. What I'd like to do then is I left you with number 28 yesterday, and I would like to work that problem out for you. Okay, so since you have your book there, let's go ahead and let's take a look at number 28 in your book. I want to work that out with you because this is a problem that is an interesting problem. It helps us to review what we talked about yesterday, which is how do we get obtain the product, the amount, what we'll call the theoretical yield in just a moment, how we can obtain that amount of product, predict the amount of product that forms from a chemical reaction if you're given the amounts of reactants. Okay, so let's go ahead and let's take a look at number 28 in your book. So go ahead, while I'm writing this problem out for you, flip over to number 28 in chapter 12. Okay, so let's go ahead and write this down. We have 2 moles of acetylene, okay, gas. We're going to combust it with 2 moles of oxygen gas to form 4 moles of carbon dioxide gas and 2 moles of water vapor. Okay, so that's the balanced equation that was given to us in the problem in number 28. Okay, so let's go ahead then. And like I said, what you always want to do is make sure you write down what you're given. Okay, so let's go ahead and let's list what we're given. Okay, so we're told then that we're starting out here. The amount then is going to be 2.40, and make sure you make note of this. This is moles. Okay, moles of acetylene and 7.40 moles of oxygen. And what they're asking us to solve for then is how much water will form. How much water will form when this reaction is run. Okay. All right, so to start out with then, make sure you remember for these types of problems here, we always want to solve for the limiting reagent first. Okay, and the clue that I can offer you then when you do these problems is that whenever they give you the amounts of both reactants, you will have to solve for the limiting reagent. Okay, so again, if they give you the amounts of both reactants, Doesn't matter what how they describe the amounts, whether it's in moles, mass, or volume. If they give you the amounts of both reactants, you, for the most part, will have to do the limiting reagent calculation. Okay. All right. So with that said, then with the limiting reagent calculation, choose one of these two starting amounts and solve for the other one. Okay. And calculate for the other one. Doesn't matter which one you choose. I'm just going to arbitrarily choose this amount here. So I'm going to say then if we have 2.4s and convert and convert to find out how much oxygen is needed if we have this here. So I'm doing the conversion between moles of acetylene to moles of oxygen. Okay, all right. So we have then 2.40 moles of C2H2. Okay, and we want to calculate for the moles of oxygen that's needed. Okay, so this is a moles to moles conversion already, folks. So all we need is the mole ratio. So let's go ahead and plug it in. 5 moles of oxygen for every 2 moles of acetylene, C2H2. You plug that in, and you'll get your value of 6 moles. So this is the calculated value of oxygen, okay, that we would need. So this is the calculated value. If we started out with 2.40 moles of C2H2. So what do we do with this value? We compare that to the given value here. So the given value, given, because it's given to us in the problem, okay? So the given amount of acetylene here is 7.40 moles of oxygen, okay? And the calculated amount of oxygen that we just calculated for, because we're going to compare this, is 6.00 moles of oxygen, okay? And so therefore, the given amount is greater than the calculated amount, which means then in the end, what does this mean for us? We have more oxygen than what is needed to run this reaction. So oxygen is the excess reagent. That's what we are able to determine from this calculation. But we don't need to know we don't want to use the excess reagent to find out how much water forms. We need the limiting reagent. And so what's the limiting reagent? If oxygen's the excess, folks, the only other reactant here is C2H2. That must be the limiting reagent. So that's what we will use to carry out the second of the two calculations here, okay, which is to find out the amount of water that forms. Okay, so let's go ahead and write that in. So we're going to again start with 2.40 moles of C2H2, and the conversion this time now will be, and they asked us for grams of water that will form from this amount of C2H2, okay? All right, so we already have moles here. The first conversion factor is going to be the mole ratio. This time it's going to be a 2 to 2 mole ratio. So this is going to be 2 moles of water for every 2 moles of C2H2. And then we need the molar mass of water in order to calculate for the mass of water, and that's going to be 18 grams of H2O for every 1 mole of H2O. Okay. All right, so you plug that in then, and hopefully you plug it in your calculator correctly. But please make sure you check my answer. Just comment if you got a different answer. Okay, and I get 43.2 grams of water, and that's how much water will form. Okay. All right, so we started out this period, and we've pretty much used almost all the time this period, just kind of reviewing what we've had, what we've gotten done up till this point. So, folks, up until this point, then please make sure that if any of these calculations, any of these problems that we've done so far, you're not quite clear on, please make sure you come by and get that extra help this afternoon with during our Zoom tutorial. Okay. All right, but we got to continue on then, and we got to try to finish up this chapter here. So what can we do with the numbers here that we've calculated so far? We can obtain what's called this percent yield. What this percent yield is, well, I'll talk about in just a moment, but it's a very simple calculation. It's a percentage. So that means we're going to compare a ratio and then make that percentage out of 100. Okay. All right. So with that said, then this is the ratio of what we call the actual yield to the theoretical yield. Okay, and we're going to express that. So the ratio then is going to be actual to theoretical. I'll define those terms for you in just a moment. Okay. But make sure you understand this. This is basically a measure of how good the reaction is, how efficient the reaction is going to be. And like I've shown you here in the second bullet point, the percent yield in real life, never 100%. You will never achieve 100% yield that in real life when we run these reactions in lab. There's so many things that can go wrong, and I'll point out a few of those things in just a moment. Okay? But with that said, then we want this number because we want to determine then how close, how good is our reaction. The closer our percent yield is to 100, the better the reaction was, the better our work was, the better that the reaction, everything was good for that particular reaction. Okay. All right, so we want to be able to calculate for this, though, even though we don't expect to get 100% yield, we want to be able to calculate for it. And so what is this actual yield? What is the theoretical yield? Well, the theoretical yield is what we've just solved for. We take the limiting reagent, we find then how much product will form, and that's the maximum amount of product that will form. That is the goal for our reaction. That is the goal. That is the if everything went perfectly, if we lived in a perfect world, that theoretical yield then that is the maximum amount of product that will form. And again, since our percent yield is never 100%, the theoretical yield will always be something that's a little bit beyond what we'll be able to grab. Okay, so with that said, then this is a calculated value. And so we calculate for the theoretical yield from the limiting reagent. And that's what we just did there. Okay? The actual yield, on the other hand, is the amount that we actually obtain when we carry out the reaction. When we carry out the reaction, we finish it up, we work it up, we isolate and we purify our product. That is the actual yield. So this is experimentally obtained. This is a value that we would get in lab. Okay, and so for our purposes in class here, and unfortunately, I'm hoping that we will be able to run eventually get back to class and run a chemical reaction here. But in the problems that we're going to do, the actual yield is described for you in the problem. And what you have to be able to do as part of this problem here is you have to be able to identify that actual yield in the problem itself. And that's going to be something you have to practice doing. But for the most part, it's pretty straightforward. They will tell you what the actual yield is going to be for the most part. Okay. All right. So what are some reasons? And I'll just finish up with this here. What are some reasons? And then we'll work out a few of these problems tomorrow. Okay. But what are some reasons that the actual yields are lower than the theoretical yield? Okay, well, I'm shooting way over time now. Let me go ahead and do this. We'll go over this tomorrow. I'm going to assign you one more problem to do that'll give you a chance to practice calculating for these theoretical yields. And again, to do that, you just got to take the limiting reagent and find the amount of product will form. So you got to practice that, folks. Okay, and we'll continue and we'll talk about these percent yields tomorrow. Okay. All right, folks, very good. Again, hope come by after school today, get that extra help if you need it. Okay? And then we'll finish up with this chapter at this point. Then we'll finish up with the chapter tomorrow. Okay. All right, folks, have a good day, and I'll see you tomorrow.